Right, welcome back. Today is week 8, Tuesday, 5th of October 2021. So in today's tutorial, I would like to discuss tutorial 4. Now, you can find the solution of tutorial 4 in this YouTube channel. And if you go through it,
through my online store alone, we've sold over $500,000 worth of spices. That's so crazy.
There are two videos. These are the two videos about 2 hours, where the first video is question 1 to 8, and then question 9 to 16. Now, I have also shown you the breakdown of the time, so you can jump to exactly which one you need, and that should help you speed things up. Okay, so go through it. Right. So because I've done all the questions, then I think that there's no point that I would go through the same set of questions. Instead, I would take questions from you, as well as maybe do some discussion, other kind of discussion. So what kind of discussions I'm interested in? Maybe I will point to you what are the things I see are difficult for these tutorials, and then we can then discuss. All right, so let's say these are the questions in tutorial 4, and I'm going to go from maybe the back. Okay, yeah. All right. Now, when I read all these questions, I realized that you guys need to know a lot of terminologies regarding linear algebra. So first, C of A means the column space of A. And A is a matrix. So that's C of A. So that's one. So I'm going to keep a few of these, and then I would then start to describe them after I keep a few of these terminologies. The other terminology is here. N of, again, a matrix. Here is the null space of matrix D. So you realize that, and here again, back here again, is the column space of D. Right, so let's push on and see what other terminologies are expected of you. Basis. So you realize that to learn linear algebra, you are actually almost learning a new language with a lot of terminologies, and you have to become very familiar with these terminologies to read the textbook. Span of a set of vectors. So not only the word you must understand, but its usage. So span is with respect to a set of something, a set of vectors. And a basis is respect to a matrix. So a basis for a matrix. A span is with respect to a set of vectors. Of course, then this is the typical one, the linear dependence among a set of vectors. Span of a set of vectors. The basis, then remember what I said about basis? The basis is for a space, a vector space. So if you are not careful and you just know the name, a basis, a span, or linear independence, and you forget the relationship of that word with what you need to, how is it used for, then you're missing quite a lot. Okay, so once I've highlighted all this, then we're going to try to maybe explain them one by one. Okay, maybe I'll use, let's see, how about this one, span. Let's begin with span. So typically we'll say a subspace is spanned by a set of vectors. And when we say the subspace is spanned by this set of vectors, we are saying that we can use, or we can create the set of all linear combination of these vectors. So that's all. The word span of V1, V2, V3 means the set of all linear combinations of V1, V2, V3. What does linear combination means? Means alpha 1 times V1 plus alpha 2 times V2 plus alpha 3 times V3. What is alpha? In our typical case, alpha is the real number. So this is how we use the word span. So something is spanned by this means that we are creating linear combinations of all these, and we call them a space, a vector space. So you have to understand the word space and subspace. So what is a space? A space is a set of vectors, and then you have all these rules of vector addition, scalar multiplication, closure, and things like that. So space is nothing but a set of vectors behaving in a certain way. All right. So I would now maybe pause to take questions. Now, in this question, we are given 3 vectors. But these 3 vectors live in the R2 space. So you realize that actually, we do not need 3 of them. We want to find a basis. We want to find a basis for the space, the subspace H. What is H? H is the space spanned by these 3 vectors. Means any linear combinations. Now, can you see the relationship between the first V1 and V2? So V2 is nothing but minus 2 of V1. What about V3? Let me find out V3 for you first. What was my results? In V3, what I get is that I realize that the second vector, minus 4 and 10, the second column vector is related to the first vector, but the third column vector is not dependent on the first or the second column vector. So by Gaussian elimination, I find 2 pivots. And these 2 pivots shows me that these 2 columns are independent. The number of pivots is 2. This will also tell me the dimension of the column space of A, because the word dimension means how many. How many, then how many what? How many vectors are there in the basis? How many independent vectors are there? There are only 2. The column space of A has only 2 independent vectors. The dimension of the column space is the dimension of this subspace is equals to 2. So that's the answer. So if you do not know all this terminology, you might be confused and say, the subspace of H is spanned by these 3 vectors. Therefore, the dimensionality is 3. That's totally wrong. The word dimensionality only applies on a basis. So first, from this subspace, we have to get a basis. To find the basis, we have to get rid of the dependent ones. We have 2 of them, So there are only two vectors in the basis. Okay, so I will stop now and pause and take questions. Right, now we try to work on tutorial 4, question 12. And here we are going to explain some terminologies, and the terminologies are these. What is the column space of A? What is the null space of A? And what are the dimensions of this null space and column space? A is a 2 by 4 matrix. What does column space of A means? The column space of A can be written as this, and it is nothing but, so after a while you realize that it is always a set of something, okay? It is the set of all. So the word space, right, will at least hint to you that you're going to get a set of vectors. The set of all linear combinations, and as the name says, of what? The columns of A. So if we call this V1, and this is V2, this is V3, and V4, then this is nothing but alpha 1, V1, alpha 2, V2, alpha 3, V3, and alpha 4, V4. And you must say alpha I equals to 1 to 4 belongs to the real number. So here we are talking about the real vector space. In more advanced courses, alpha can be the complex number. So then we'll be talking about complex vector space. Then the notation to be shorthand is now alpha I equals to 1 to 4 Vi. Okay, so the notations are all the same. All right, so that is column space. It's another name. So you realize that I'm trying to share with you how many names there are. The column space of A is the set of all linear combinations. So this is one description. Another description is, so the word set of all linear combinations is the span of the columns of A, isn't it? What does the word span means again? Remember, that's the first one I described. The word span means the set of all linear combination. So the word span is nothing but this guy here. Okay, so this is what we want to figure out. What else? There is another name for column space of A. Okay, believe it or not, it is range of the transformation matrix A, and sometimes it is called the image of A. Have you all seen these two words, the range and the image? Guys, anyone? I'll pause now and take. Okay, you have. So the range means actually exactly the same, the linear combinations of A, the linear combinations of the columns of A. All right, so you realize that, hey, it is a very tricky affair. You have to know all these names and use it, interchangeably. All right, so now let me try the column space of A first before I do the dimension. The null space, sorry. So now I am going to describe the other guy. The null space of A. So the null space of A, so the null space is with respect to a matrix, okay? In our course at least, the null space of a matrix. But then you'll be thinking, what does this mean? Now so this symbol comes out. So again, null space is a set of something, vector x such that, so this line is such that Ax equals to 0 vector. Now this is a 2 by 4 matrix. So X must be, in this example, this is a 2 by 4. A can only be multiplied by a column vector. Oops, let me get. So X is R4. This guy is 2 by 4. This guy is 4 by 1. This guy is 2 by 1. So that 0 there is the 0 vector with 2 elements. So null space of A has nothing to do with A in that sense. It didn't come from A. It comes from X. The use of A is to make this condition AX must be equals to, so this is the condition. This AX must be equals to 0. So the null space of A is X, the set of X that this is true. Now, there's another word for the null space of A. So I will write in green now. It is sometimes called the kernel of matrix A, representing some transformation. So there are so many names, right? But they all mean the same thing. And that's why people are confused. There are maybe some very fine distinction between the word kernel and the null space of matrix A. But I mean, for our level, we are okay to use null space of A and kernel of A are the same thing. All right. Now, let me pause. So we are given this matrix A, and in fact, it is in already reduced echelon form because we can see the 2 pivots. So we know that these 2 columns are independent. Therefore, the column space consists, the basis for the column space consists of these 2 columns. The number of pivots are 2. The dimension of the column space equals to the number of pivots equals to 2. Number of free variables is the dimension of the null space. So it is 1, 2, 3, 4. 4 columns minus the 2, what do you call that? The 2 independent column. So we get 2 free variable. The null space dimension is the dimension of the free variable, or how many free variables there are. There are 2. Okay, so this is we're going to go into something called the rank nullity theorem. And then you'll figure out that this is the relationship between the rank and the nullity and the number of columns there are. Okay, so what else do we have? Okay, so now we're going to talk about the rank nullity theorem. And in this level, in this course, we are studying everything with respect to a matrix, where the matrix, for example, A is going to transform AX to something else, Y. And we're going to check the rank nullity from the perspective of the matrix A. Let us have a matrix of size m by n. So this guy is the number of rows, and this guy is the number of columns. Now, so let us now begin to understand each of these words. The nullity of A, it is with respect to a matrix in this course. Okay, the nullity of the transformation matrix A, because A is going to be used to multiply with something else, A times X. So A behave like a linear transformation. So the nullity is with respect to A, the transformation matrix. The definition of the nullity is that it is a number. So this is a number. How many dimensions, how many vectors there are. The word dimension here is how many, or the word more technical term is called the cardinality. But here we just say the number of vectors. I guess it's maybe independent vectors in the null space of A. So what does the dimension of the null space of vector A? Maybe it'll be easier if you say the number of independent vectors, or in fact, I don't even need to use the word independent because I'm going to use another word to describe the word independent. And the word is the number of vectors in the basis of the null space of A. Okay, so nullity is a number. Nullity is going to operate on a matrix. Nullity is a number, so it is the number of what? The number of vectors. The number of vectors from who? It is the basis, the set of vectors that spans the null space of A. Okay, so you realize that to answer this question, I mean, there's a lot of vocabulary going on here. All right, what about rank? Maybe now I use rate again. Rank. Find out what the definition of rank is. It's the number of independent rows, which is very interestingly is equals to the number of independent column. Okay, so that's a very surprising fact. If you say I only, let's say I have a m by n matrix. If you say I have three independent rows, you know, so m by n, then you have three independent columns. So it's 4, if you have 4 by 2 matrix, for example, then the maximum number of independent row and column is the smaller number. That's the maximum. Okay, if you can reach the maximum, then this matrix is called full rank. If you have a 4 by 2, so now I'm going to draw for you a 4 by 2 matrix, guys. So this is 4 rows. This is a 4 by 2 matrix. Yes, so you see that this is for 4 by 2 matrix. But how many independent columns are there? There's only, so number of independent column equals to 1. Number of independent row also equals to 1. Right? So even though the matrix is 4 by 2, the number of independent, even though it is 4 by 2, what happened is that the number of independent row, let's call it R, and R is actually, it hints at the word rank. The number of independent row and independent column is only 1. So this matrix is not called full rank. Okay, so the word full rank is used in this context. So the word rank means how many independent rows and columns there are. The word full rank means that this matrix achieves the maximum number of independent row or column. So in the 4 by 2 matrix, the maximum number it can achieve is 2. However, this guy only has 1 independent row or column, therefore it didn't achieve full rank. Okay, so right, so there's rank and nullity for you. Okay, now I will pause now